Welcome in Core. TRAPPIST-1, a red dwarf star just 40 light-years away, has long been a key target in exoplanet research with 7 O-sized planets, 3 in the habitable zone. However, their high activity, flares, star spots, and magnetic storms have obscured our view of these planets. Now, thanks to the James Webb Space Telescope, astronomers have unveiled its magnetic field for the first time. This breakthrough could lead to more accurate exoplanet atmosphere measurements and has broader implications for studying stars like it. It all began with 4 massive stellar flares. Keep watching this video to know more about this topic. The Discovery TRAPPIST-1 is an ultra-cool M8 dwarf star, much smaller and cooler than the Sun, but magnetically active to an extreme. Its planets orbit close in, meaning they receive constant exposure to flares and magnetic disturbances. On such a star, surface features like cooler star spots and hotter factlet alter the star's light output. When a planet transits, these features can distort the measured spectrum, complicating any attempt to determine the planet's atmospheric composition. For years, the exact spectral profile of TRAPPIST-1's magnetic features was unknown. Without it, astronomers had to make assumptions when removing stellar effects from planetary data, a process that could either hide important atmospheric details or produce false signals. In this new study, Valery Vasilev and colleagues at the Max Planck Institute for Solar Research used JWST's 1’s instrument to monitor it during 4 stellar flares. Time-resolved spectroscopy allowed them to track how the star's light changed before, during, and after each event. After each flare, they noticed a persistent brightening in certain wavelengths. Initially, it might have been dismissed as lingering flare afterglow, but the timing and spectral behavior didn't match that pattern. Instead, the data suggested the flares had disrupted and erased dark regions, essentially removing star spots on the Sun. Intense flares can destabilize sunspots in much the same way. By comparing spectra before and after the flares, astronomers directly measured the disappearing features on it, finding the spots were only a few hundred Kelvin cooler than the surrounding photosphere. This is the first direct spectral measurement of a feature on an M8 dwarf, providing crucial baseline data for future observations. Scientific importance and theories. The key outcome of this work is that astronomers can now subtract TRAPPIST-1's magnetic signature from planetary spectra with precision for planets in the habitable zone. This means reduced uncertainty and fewer chances for false atmospheric detections. Before this study, stellar contamination was one of the biggest obstacles in exoplanet research around active red dwarfs. Without knowing exactly how star spots alter a star spectrum, it was easy to mistake their effects for atmospheric gases such as water vapor or methane, or to overlook real signals hidden by the star's variability. The findings also advance our understanding of stellar magnetism in ultra-cool dwarfs. Despite differences from the Sun, it appears to share a similar process in which powerful flares can erase surface features. This points to common fishing behaviors across different types of stars. Understanding the life cycle of these regions is important for habitability studies. Star spots can change a star's brightness over time, influencing planetary climates and atmospheric stability. If flares periodically remove them, this could mean more dynamic but potentially less predictable environments for orbiting planets. Since red dwarfs make up most of the stars in the galaxy and many host small rocky planets, the implications extend far beyond it. The same observational method could be applied to other active systems, enabling better atmospheric characterizations across a wide range of targets. Since red dwarfs make up most of the stars in our galaxy, this method is widely applicable. Observing similar flare events on other systems could reveal behaviors across a range of stellar types, enhancing the accuracy of exoplanet studies in many different environments. Implications and what's next with the spectral profile of TRAPPIST-1's magnetic features now known. Transmission spectra of its planets can be corrected with far greater accuracy. This improvement is particularly important for the search for biosignatures, gases or combinations of gases that could indicate life. Without such corrections, a star's influence could mimic or obscure these signals. The technique is widely applicable. Other active M-dwarf systems such as Proxima Centauri and LHS 1140 could be studied in the same way. Timing observations to capture flare events could become a deliberate strategy, turning moments of high stellar activity into opportunities for surface mapping. For TRAPPIST-1 specifically, this work allows better modeling of the radiation environment its planets experience. Although strong flares still pose challenges for habitability, knowing exactly how they alter the star's output improves estimates of which worlds might retain stable atmospheres. Future research could expand this method to other wavelengths, particularly ultraviolet, where stellar activity has a strong impact on planetary atmospheres. Next-generation observatories like the Extremely Large Telescope, ELT, could also provide more detailed spot mapping and track how magnetic features evolve. By integrating these new measurements into observation strategies, astronomers can move closer to the goal of distinguishing true planetary atmospheric signal from stellar interference, a necessary step in determining which worlds could support life. This reframes how astronomers view stellar activity not only as a challenge, but also as a means to study and correct for the very phenomena that complicate planetary observations. The detection of TRAPPIST-1's hidden magnetic features marks a breakthrough in exoplanet research. For the first time, astronomers have measured a feature on an M8 dwarf, enhancing the accuracy of atmospheric and habitability data for its 7 planets and others orbiting active red dwarfs. What was once an obstacle is now a valuable tool in the search for life. Stay tuned as we uncover more about the stars and planets in our universe. Thanks for watching. Cool.